So I'm going to talk now about our work in Julia concerning battery simulation. So I start with a overview of the mechanism, the working mechanisms, principles in the battery. So here is I want to give credit to for the illustrations to this person, Jordan Gisidi, which published a YouTube video. You can find the link there. So the battery is made of two current collectors on the sides. They are metal, highly for use for their high conductive properties. Attached to those, you have grains on left and right, and this makes the electrodes. The grains are the active materials, carefully chosen for their properties. In between, you have like a membrane, light membrane, and it's called the separator. It prevents the two electrodes to touch each other and to isolate electronically the electrodes. Yes. So here is the picture of you can see singled out a lithium atom. It's the core is in yellow, and outside the electron is represented as a green shell. And then the electron, the atom loses its electron, becomes an ion, and goes into the electrolyte phase. Yeah, I forgot to mention the electrolyte phase is what it's all over between the grains and in the separator. It's a liquid. And then the electron goes into, you can see the blue dot goes up into the wire, takes the way toward circuits, while the lithium travels to the other side to reach the other electrode. And it does that because the energy you get in this other active material, it's much lower than the one he had in the previous. So we are now in the discharging phase. And the energy, the lithium takes this long trip because its energy will be lowered. And we know that energy is conserved. So the energy that is lost, you gain it through the circuits. But there are parts that are lost. This is thermodynamic. And the design, a good battery will be the one that minimizes this loss. And then it gets inside the new material, and that's where and recover its electron and becomes again an atom in a position with the ion. The picture is a bit okay. It was a bit a cartoon, so a bit more realistic picture is that you have the same components, and here you see all the lithium that diffuse, that goes from the solid phase, the electrode, into the electrolytes, and they will then travel around throughout the separator here, which is not represented. Okay, so I was just telling this this story of the lithium going from one side to the other. So you see many like a flow of ions going through the battery. Okay, and then at the end it goes inside the core, and then it stays there. It's diffuse, it's solid diffusion inside. So why do we do battery motivation? So typically it's about these digital twins. So we like to predict a state of health. Okay, state of charge. How much is there in the battery left? You want to know that with measure that, and the state of health, the degradation processes we have to include in the model. And also the other thing, which is state of safety. Often it's a bit different state of health. You want to also stay away from regimes where things can just be dangerous. Design optimization for specific use. Design of test. So this is a project, BatMax, where we want to have less tests and better tests. And also battery monitoring system, embark tools to say how you should operate your battery. And informed on a model, on a digital twin model that give you insights. What about the model? So first we started with this this porous medium. So here in the blue is the electrode, the solid phase electrolyte, and we are going to simplify a lot this geometric representation, which is common to do in porous media in general. So we forget about this. We just give a volume fraction, the amount, the proportion of liquid and solids. It's defined like that. So all this fine representation is reduced to one scalar variable. It's a coarse approximation, good enough. And then at the same place, you're going to have electrode and electrolyte. At a given rotation x, you're going to have a concentration of lithium for the electrode and electrolyte, same point x. We want also to model the solid diffusion inside these little grains of material, of active material. And this is done using a pseudo particle model. At each location x, we gave like a ball, a circle, a sphere, where we represent the distribution of lithium. Because the lithium, it goes from the side, and it's going, all the reactions are interface, surface reactions. And then the lithium has to leave the way to other lithium coming in. So it's going to diffuse inside the solid. I'm still in? Okay. Yes, so we use this model. So all about modeling. So at the end, what is the picture? So we have different domains with different variables. So here 5 domains, 2 current collectors, the electrode and the electrolyte. In each of these domains, you have some variables, which are the concentration and potential. Electrical potential in phi, each of these domains, and the lithium concentrations in 3 of those domains. For the active material, say it depends on x, the spatial coordinate, and r, the coordinate in this pseudo particle. Okay. And what is the governing equation are basically mass and charge conservations in each domain. And the interaction between the domains can go at the boundary of the domain between the current collector and electrode, so boundary exchange term, boundary terms, and exchange terms. This is really the most fundamental one, the chemical reactions. So the lithium goes from one component, the electrolyte, inside the electrode, the active material. Typical form of the modeling equation, so that's a partial differential equation for conservation laws, which look like this typical form, which I just may recognize at once. So you have like a hyperbolic, or so parabolic and hyperbolic. And this is why we ended up in the battery business, because these conservation equations are very similar to the one we had in the reservoir. So at the end, we use finite volume discretization, full implicit scheme for robustness. And for each time step, well, we have to solve a system of nonlinear equations, where the unknowns are in each of these discretized domain. So here you see the different domains, and some of them overlap. So there will not the electrolyte, it's not represented with its own color because it overlaps. And each of these segments, you have concentration and potential as unknown. So then it comes to the Julia part. So we have, but BATMO was developed maybe 34 years ago. It was developed first, it's coming with 2 flavors, MATLAB and Julia. We started with MATLAB because we had a lot of code which is, for reservoir, MRST, MATLAB Reservoir Simulation Tool, which gave the basis for us to develop this. And then we had, at the same time, there was an initiative in Julia, also for reservoir, and we wanted to port this to our battery code. So now it's registered in the Julia General Registry. We have the address here. So it's based on Jutul. So this is the experimental Julia framework for fully differential multiphysics simulators based on implicit finite volume methods with automatic differentiation. And this has been developed. Also, the main developer here is working with us in our group. So, what is the Julia Jutul? What does it bring? So, it's a generic interface for system assembly. Generic in the sense that you have like this interface invites you to declare your primary variables, so the concentration and the potential. You say, okay, these are my primary variables, and then I have other variables. They are made of the reaction rates, the diffusion coefficients, the electronic conductivity of this thing depends on the primary variables, 2 functions, and have to be computed. But they come into the category of secondary variables. They are local dependent. And then there is a mechanism here based on the setup of dependency graph, which sets up automatically the dependencies between this local dependent variable and call them in the right order, call the functions, updating function in the right order. So you have optimal caching of all these variables. That's just to ease the implementation. And then we know from the other, it provides also a way to declare and to set up conservation equations. So you give the accumulation terms, the source term, and the fluxes. And in addition, it was added actually also for the battery work, like a multi-model. So all these operations that are done above, you do it for each of your domain: electrode, negative electrode, positive electrode, electrolyte, and so on. The output is that when you have set up this, it will send you to Digiwell will make the assembly for you. So set up an optimal way to assemble all these equations. Assemble means compute the residual equation and the derivative, because we use Newton. And this is done in the fastest way, very fast way. So then it brings also full AD framework, also for the parameters. So when you design the battery, things I've talked about this state variable, potential and concentration, but also the length. This is typically a given parameter. And now other things are just porosity is given, but at the end we want to optimize the design of your battery. You are going to change this, and you want the sensitivity. You want to differentiate those things, and this is packed in. So Digiwell has been implemented for Digiwell Darcy. So this and now it matches the speed of which is oil and gas recovery, and match speeds of commercial simulator. There's a big effort on that, and to match the speed is not easy. And the thing is that there's been done some work to fine-tune the solver, and especially the code is equipped with a comprehensive set of performance measurement. We are going to see one of those reports, which is essential for future development. We say, okay, what happens to, you want to know what your simulator is doing to be able to improve on it. It's not, so you need to measure its performance at different steps to see where you have to work for improving it. So we have a JSON input interface. So we work on that. So it's that all our the input parameters are given through a JSON file. So okay, this is for the heat, for energy, and the reaction rate constants, guesstimated. I don't go into that, but this is this nice standard format we have worked. Important. And then yes, so we have our own colleague and also initiator of this work, Simon Clark. Trondheim is battery modeler, and a lot of work developing an ontology just to standardize the terminology. Ontology is about define what the words that are used, and in also algorithmic way, machine readable way, and big effort. And we try to fetch from there the description of the materials and to reuse this work. So then this is the first one. So let's see. Okay, let's see. Okay, let's see now if I have it. Okay, so now I'm in Julia. So I've set up this before, and then if I run this, so I use this package batmu, and then I run this battery stuff. So let's run it. So it's fast. So of course you have no comparison. So but it's much faster than our MATLAB implementation. I think 100 times. So 2 orders of magnitude. And then you see what I was alluding to. So you have the like a report about what has happened. How much did you time to evaluate the properties, assembly, the linear solve, convergence. What we can see is that I would make the comment that it's pretty well balanced, which is good. For example, in our MATLAB implementation, It's not the linear stuff that takes time, the assembly. Computing all the ADI stuff, that would take 90% of the time. Yeah, okay, it's better. The assembly is fast. Okay, so then oh yeah, I have the plot. So simple plot. So here, this is about the output. So we discharge our battery at a constant rate. So rate is current is ampere. So we draw the charge, constant current, and you see the evolution of the potential. So it's stable for a while, pretty flat. That's why you have a battery for. You want this flat plateau, and then at the end, the battery is empty and the potential drops. Your battery is you have to recharge it. All right, and this I comment already. So about Julia, comment about the Julia things. This is what we are here for. So there are several important functional parameters in our model. For example, one of those is are the open circuit potential. I haven't. It's about how much the battery is going to fill to be filled in by lithium, the active material, and then the more when it's filled, the attraction for new lithium drops. This is the open circuit potential, and it's a function and depends very much on your material. It's going to. This is what about. You use graphite. So each of those, graphite, NMCA, all this material, you're going to bring their own curve. This is the most important parameter, and it's a function. And here I have so I have for example, an expression they like in the field. They like for some reason they like to make probably for publication, but they use like this expression like this algebraic formula. Okay, string. So it's at first it's just a string, but from this string you have to make a function. And this was a issue because at first we used eval and invoke latest to macro. Eval is like you have a string, and by evaluating you make it code. It's like a macro process. Invoke latest to get, because there are some subtleties in eval, but this was not compiled. And this function is called very much many times. And then we had a substantial drop in speed. So then it's like, okay, well, all this work over all this speed. Like now it's become it was 2-3 seconds. Solution comes from this. This is a word edge problem that you cannot really compile a function that is created on the spot. It cannot be compiled naturally. It's some problem, but there are workarounds. And this is something by CML, so this initiative is rather big initiative, which gives you this tool, which solves this problem. I think good to know, and we had just I can. That's why I'm talking about it. So you see, you fetch a string. From string, you compute an expression. So this is the macro language of Julia, and then from the expression, you run this macro run, which is going to produce a function compiled. And then since you call it thousands of times, you see the other thing I'm going to talk now. It's about we have this Julia code and the interface we have had. So so we implemented a Julia bridge, can be used from MATLAB, and here I can go through the command. So if maybe it can inspire you in your work if you need such things. So we use the daemon mode. And the daemon mode was quite rather easy to set up. It always takes time. You have to struggle, as you know, the programmer life. Okay, but still, at the end, can be summarized in this. So you start Julia. You give a given your own project, or you have your dependency descriptions on your manifest, and you start the daemon mode, and you say serve. Okay, and then you can call with an executable using daemon mode, which is here. Daemon mode, run args. So this comes from daemon mode. This is the port, and you send a function with its argument. Daemon.gl is the function we have implementing, and this is one argument. Run the simulation, and this is just the steps you have to do to use this server. And then we send the data through files, and from the MATLAB side, This is what just was done. So you server manager, you read the JSON input, you see all the parameters I've shown you, they describe fully your problem, and you send it to Julia, and you get the result in a MATLAB format. Sorry. Okay. I think I cannot show you examples because it's I need a VPN. So we have the web. We also designed a web app. So that was work done from colleague Raynaud and Drix in Trondheim. So which connects to Batmo Julia. So this is a nice way to expose your work. Somehow you have the solver, and then there is a web app. I'm going to show you what it looks like. It can be run. Yeah. So the application has been. She has kind of tried a different setup, and she ended up using happily. She was happy with the setup that using Docker containers that do then different things. In Jenny, so this is Julia package for web app, and she used that to run Batmo. And then there is Nginx, a production server. This I will not comment on. Locally, actually, I think I don't use it locally. It's just when you want to. It's yes, to make it a very robust server when you want to deploy it. And Streamlit, that's the web app design. So the interface, the GUI side on your browser side. And the two Docker, they communicate with each other through port, like a REST. And I'm just going to. It's a bit small, maybe. So if you do, so I just if you see the way it's done. So this is the Jenny. So I think a pretty lean interface. So you set up routes, which is the method of post. So you are going to post the data to this run simulation routes. So Streamlit is going to use this this route. And the first step, okay, you load your data in JSON. You run your model. So this is just a wrapper against the Batmo GL code. And from the output, so we process it in HGFM, and then we send it as a response. And on the other side, the web app is going to Streamlit is going to read this response. So we send that. I should have shown you the line, but I think I will not. Let's see. I'm not sure if the thing is running now, but we can. Let's see. So this is how the web app looks, and then you run the simulation. Let's see if it's okay. It's running. You see here. Okay, working. All right. So I think it has run now. And then you can visualize the results. No, it didn't run. So we do it one more time. That's okay. This one is just to scare you. Or me, more me than you. Okay, so it's working here. Okay. I hope now it's okay. So you go to the result to see the visualization. And here you have it. So here we have another scenario where you use discharge battery and then you charge it. There are different protocols described here, and here you have some nice visual tools. So this is from Streamlit. Now it has retrieved all the data from Julia, and so this is from Jenny, and this is so here you can select line. I think I can add more negative electrode concentration. So inside the battery. So you see here, I have at this stage, I'm discharging, okay? And this is the left and right. So you have discharged more the right part of your, so this is the negative electrode on the left side. And the lithium are moving from left to right, but the first one to leave are the closest, and you see that. So there is a gradient in the concentration. You observe, and this is the one that is computed from the simulation. Okay. So I conclude. So the use of Julia solved for us fundamental speed issue we had in our MATLAB implementation concerning the assembly. Assembly was too slow compared to what we wanted to have on other codes, so it didn't look good. The Julia implementation was integrated in different interfaces. It's what I showed you. It's good for motivation and to MATLAB. So you can use your code in Julia in different ways. And this, then you appreciate to have put effort into that. That's good. And we still we have this double language thing. That's okay with Julia for speed, and a language for speed and a language for prototyping, MATLAB Julia. So we are still interested in using just one language. So, but we are still not there for historical reasons, and but we want to go there. I think it makes sense to go there. And I want to think this is the project we are part of. So I have to think more. So this we are part in 4 EU projects, which are listed here. So I want to think this for the fundings. And this ends my presentation.